Segment 8a, Kepler and Kepler's Laws, how he derived them. I feel very strongly that it's important not only to know what the newly discovered laws were, but something about how they were actually derived. And in this segment we'll explain something that you won't find in your textbook and you may not find in any other textbook, which is an explanation in simple terms of how Kepler went about deriving his famous laws. We recall from last time the story of Tycho Brahe, who lived from 1546 to 1601 and was an astronomer at the Danish court. Tycho spent 20 years of his life measuring very accurately the positions of the planets against the stars. These measurements were an invaluable resource for trying to test models of the solar system. Tycho was not much of a mathematician, and he hired a young assistant, Johannes Kepler, who was born in 1571 and died in 1630. Kepler was hired to interpret Tycho's data, but Tycho, as you will recall from last time, had a pretty fixed idea of what the solar system looked like, this Tychonic universe where the sun orbited the Earth, but the other planets, the sun orbited the Earth, but the other planets orbited the sun. And Tycho was eventually so suspicious of Kepler and his motives that he kept Kepler from looking at the data. And Kepler had to wait for Tycho to die before he got a good look at the measurements. And in fact, there were some disputes between Kepler and Tycho's family about possession of Tycho's notebooks. This diagram illustrates the behavior of the inner and outer planets as we understand them from our observations. But this is a bird's eye diagram of the solar system. Of course, what Kepler was working with were simply measurements of positions in front of different stars at different times of night. So what we really need to know is how the problem was solved the other way. How did astronomers develop this picture that we see here from the actual motions observed on the sky? The important things to remember are, in terms of terminology of this, are the terms synodic period, which in the case of planets means the time between oppositions, that is, the time between when the planet and the Earth and the Sun are all along the same line, with the planet outside of the Sun. So it's this planet transiting then at midnight, or inferior conjunctions in the case of the inner planets, where the planet and the Earth and the Sun again are aligned, but the planet is directly in front of the Sun. The sidereal period, on the other hand, is the time it takes a planet to orbit the Sun once, that is, to be from the Sun's perspective in front of the same star again as it was on its last orbit. So here is a fairly complex derivation, and I don't expect you to understand it or know it in any detail, but I want to show you that that the tooth fairy doesn't bring Keplers solutions, that Kepler worked this out and give you some idea of how he went about it. So again, we start with the synodic period S and the sidereal period P of a planet. The angular velocity, that is the number of degrees along its orbit that it moves per fraction of the period, or per day, is 360, the number of degrees in a circle, divided by P, the period in a day. The Earth's sidereal period, of course, 1 year, and the angular velocity of the Earth is 360 over E, which is about a degree a day. So now we can ask ourselves, remember the outer planets are moving more slowly, so the Earth gets back to opposition. The synodic period is some amount of time somewhat longer than the Earth's period. In the case of Mars, it's quite a bit longer, but in the case of the slowly moving outer planets, it's only a little bit longer than a year. But the angle through which a planet moves between oppositions is just the synodic period, S, times its angular velocity, 360 over P. So the Earth moves around to where it started in front of the stars in one Earth sidereal period, E. And then it has to catch up with the planet in order to be in opposition again, in order to reach the synodic period of the planet. So the Earth moves through an angle which is S minus E, the synodic period minus the Earth's sidereal period, times the Earth's angular velocity, 360 over E. During this same time, the planet has moved through an angle which is equal to the angular velocity that it moves times the synodic period. It's been going that way for one synodic period, so s times 360 over p. So we can do a little algebra to this to get to our conclusion. If we divide both sides by 360, we have s over e minus 1 is s over p. We can then use a trick which most of you know, which is we can write 1 as the same thing over itself. We write it as s over s. And then we can divide on both sides of the equation, and we have 1 over e minus 1 over s is 1 over p. So we see from things we know, the sidereal period of the Earth, 1 year, and the synodic period of the planet, the time between oppositions, which is easy to tell. It's the time between when it's directly overhead at midnight and the next time it is. We can derive the sidereal period of the planet, the time it takes to go around the sun. Now, what we can do is we can take this whole series of observations and we can draw lines from where the Earth is to the distant stars at the same time in the planet's orbit. So when the planet is back at the same place as it was, because it's one sidereal period later. We have measurements of the planets at many different times on their orbits, so there are many series of observations where we can get this. So each time these lines cross, it's marking the position of the planet in units of the Earth's orbit. So these two crosses that you see in this picture are just two of the positions of an outer planet, say Mars. But because we have measurements over 20 years, we have many, many of these. So that series of crosses essentially builds up to make a diagram of the planet's orbit. Now, Kepler's 3 laws are empirical laws. What do we mean by this? We mean that these laws are essentially a summary description of the reality. They're not based on basic physical principles, but they simply describe in simple terms the behavior of some physical object. They're just distillations of data without any physical framework. They provide a summary of the observed results.